Okay, so we're going to do a few examples involving zeros and multiplicity. So directions for the first one ask us to find the zeros and their multiplicities for the following function. So we're given the function f of x equal to 8 times the quantity x plus 3 to the fourth power times x minus 1/4 squared times x plus 6. Okay, so we want to identify the zeros. So the first zero is going to be the value that makes that first factor 0. So that's going to be x is equal to -3. And then if we want to identify the multiplicity is going to be the exponent for that factor. So that multiplicity is going to be 4. And since the multiplicity is even, the graph is going to touch the x-axis at x is equal to -3. Okay, our second zero is the value that makes the second factor 0. So if x minus 1/4 is a factor, x is equal to 1/4 is going to be the 0. And then the multiplicity of that, that 0 is going to be whatever the exponent is, which in this case is going to be 2. Again, because the multiplicity is even, that means that the graph is going to touch the x-axis at that point as well. Okay, and then our third zero is the value that makes the third factor 0. So if our third factor is x plus 6, the value that makes that factor 0 is x is equal to -6. And then the multiplicity of that 0 is the exponent for that factor. So that has an exponent of 1. So the multiplicity is 1. And if the multiplicity is odd, that means that the graph is going to cross the x-axis at that x-intercept. Okay, so let's work through this one. Directions are a little bit different here. Directions here ask us to find a polynomial function with the given degree and zeros. Okay, so if we know our polynomial function is of degree 4, and we know that this polynomial has 4 zeros, that means the multiplicity of each of those zeros have to be 1. Okay, because the maximum number of zeros or x-intercepts a polynomial of degree 4 could have is whatever the degree is, which happens to be 4 here. Okay, so if 4 is a 0, x minus 4 has to be a factor. If 2 is a 0, x minus 2 has to be a factor. If -1 is a 0, x minus -1, which is x plus 1, is a factor. And if -5 is a 0, x minus -5, which is x plus 5, is going to be a factor. Now, something that you guys need to be aware of is you can multiply out in front of this polynomial by a, which again, if we remember what multiplying out in front of a fraction does as far as transformations is concerned, it can vertically stretch if a is bigger than 1. It can vertically compress if a is a fraction between 0 and 1, and it can reflect across the x-axis if a is negative. All three of those transformations are not going to affect the location of the x-intercepts. Okay, so if I were to multiply out front by 3, that's not going to change the location of the x-intercepts. But what I want to do in this particular case is I'm going to set a equal to 1. So I don't have to like multiply my final polynomial by some value at the very end. Okay, so we're just going to assume that a is equal to 1. Okay, so what we want to do now is we want to like expand this polynomial out. So I want to FOIL out each of those two expressions and then multiply the results together. So we get the polynomial function that has those zeros. Okay, so when I FOIL out x minus 4 times x minus 2, that's going to become x squared minus 2x minus 4x is minus 6x, and -4 times -2 is +8. And then I'm going to FOIL out x plus 1 times x plus 5. So that's going to become x squared. X times 5 is 5x. 1 times x is x, so that makes plus 6x. And then 1 times 5 is going to be 5. Okay, and then I want to multiply. Again, we're leaving a to be equal to 1, so I don't have to like write that factor of a out front anymore. Okay, so I want to multiply these two trinomials together. So I'm going to kind of color code this. So first thing I'm going to do is I'm going to distribute this x squared across all three terms. I'm going to do that in black. And then I'm going to distribute negative 6x across all three terms. I'm going to do that in green. And then I'm going to distribute positive 8 across all three terms. And I'm going to do that in red. Okay, and then we're going to see what our resulting polynomial becomes. Okay, so when I distribute x squared times x squared is x to the fourth. X squared times 6x is positive 6x cubed. X squared times 5 is positive 5x squared. Okay, then we're going to distribute negative 6x across all three terms, so I'm going to do that in green. So negative 6x times x squared is negative 6x cubed. Negative 6x times positive 6x is negative 36x squared. And negative 6x times 5 is negative 30x. And then I'm going to distribute 8 across all three terms, which I'm going to do in red. All right, so 8 times x squared is positive 8x squared. 8 times 6x is positive 48x. And then 8 times 5 is positive 40. Okay, and all I need to do is combine like terms here. All right, so that's my only x to the fourth term. Here we have our x cubed term, so we have 6x cubed minus 6x cubed. The x cubed terms cancel. Okay, so there are no x cubed terms. All right, let's do the x squared terms next. So we have 5x squared minus 36x squared and 8x squared. So 5 and 8 is 13. Negative 36 plus 13 is negative 23 x squared. And then our x terms, we have negative 30x plus 48x is plus 18x. And then we have our constant term at the end, plus 40. All right, so that right there is our polynomial function. That's going to have the correct degree, which it does, that is of degree 4, and it's going to have those zeros of 4, 2, negative 1, and negative 5. All right, let's move on to the next one. Next one's going to be a little bit trickier. Okay, so for number 2, we're looking for the polynomial that has zeros at x is equal to 3, x is equal to 1 plus rad 3, and x is equal to 1 minus rad 3. And we're told that our polynomial function has a degree of 3. Okay, so again, it has 3 zeros. It has a degree of 3. That means the multiplicity of each of those zeros has to be 1. Okay, so let's go ahead and construct our polynomial here. So if those are my 3 zeros, then I want x minus each of those zeros to become factors. Okay, so the first factor is going to be x minus the first 0, 3. The second factor will be x minus the second 0. So I have to subtract the quantity, 1 plus rad 3. And then for our third factor, it's going to be x minus the third 0, which is the quantity 1 minus rad 3. Again, we can multiply that out front by a, and that's not going to change the location of the x-intercepts or the zeros. But again, just like I did in the previous example, I'm going to choose a to be equal to 1. That way I don't have to like multiply at the very end. Okay, so I'm going to rewrite this really quick. So we have x minus 3 times, I'm going to distribute the negative 1 across both terms in our next factor. So that's going to become x minus 1 minus rad 3. And then I'm going to distribute negative 1 across that 0 in the third factor. So that's going to be x minus 1 plus rad 3. Now, what you could do is like distribute all of this stuff out here. But I'm going to show you a way that's quicker in this particular case. Okay, so a faster way to distribute all of that stuff out is to regroup the second and third factors like this, where you have x minus 1 minus rad 3 times x minus 1 plus rad 3. So when you look there, you have something of the form a minus b times a plus b. And you guys should know, like, that if you multiply something times its conjugate, a minus b times a plus b, that's going to give us the difference of two squares. That's going to be a squared minus b squared. So if x minus 1 is our a value and rad 3 is our b value, then this is going to become x minus 1 squared minus rad 3 squared, which x minus 1 squared, that's x squared minus 2x plus 1, minus rad 3 squared, which is 3. So that means that entire quantity, if I were to multiply it out, becomes x squared minus 2x, and then 1 minus 3 is minus 2, which gives us like a way faster way to expand out that quantity. Okay, again, if you're recognizing the pattern, that's a minus b times a plus b, that's going to multiply out to a squared minus b squared. Okay, so all I have to do now is multiply that times x minus 3. So again, I'm going to do that via colors. So I'm going to distribute x across all three terms in black and negative 3 across all three terms in green. So that's going to make my function f of x equal to, when I distribute x across all three terms, we get x cubed minus 2x squared, and then x times negative 2 is minus 2x. And then when I distribute negative 3 across all three terms, negative 3 times x squared is negative 3x squared. Negative 3 times negative 2x is positive 6x. And negative 3 times negative 2 is positive 6. Okay, so all I want to do now is combine like terms. So we get f of x here equal to, that's my only cubed term. My squared terms are negative 2x squared and negative 3x squared. That makes negative 5x squared. My x terms are negative 2x plus 6x, which adds up to positive 4x. And then my constant term is plus 6. All right, and that right there is the polynomial that gives us those zeros and has the given degree. Okay, one more thing to talk about, and then we'll get into our final set of examples, which I'll do in the last video. Okay, so the last thing for us to go over is end behavior, which says for large values of x, either positive or negative, the graph of the polynomial, and then I just wrote the general form of a polynomial. Okay, so f of x equal to a sub n times x to the n power plus a sub n minus 1 times x to the n minus 1 power plus a sub 1 times x plus a sub 0, resembles the graph of the power function y is equal to a sub n times x to the n power. Okay, so if you have a polynomial function, the end behavior of that polynomial function is going to be the highest degree term. Okay, now there are 4 different types of end behaviors that you need to concern yourself with. The first one is y is equal to x raised to some odd power. Okay, so I just used x to the 5th power. So the end behavior of x to the 5th is going to go down and to the left and up and to the right. The next one is the end behavior of the opposite of an odd function. So y is equal to negative x to the 5th power. Well, that will be the end behavior of x to the 5th, but we're just reflecting that graph across the x-axis. So when I reflect the end behavior across the x-axis, that's going to go up and to the left and down and to the right. And then we have y is equal to x raised to some even power, which I'm going to use like x to the 4th power here. So if our function is y is equal to x to the 4th, the end behavior of x to the 4th is going to look like this. It's going to go up and to the left and up and to the right. And then y is equal to the opposite of x raised to some even power. So if we do y is equal to the opposite of x to the 4th, y is equal to negative x to the 4th. That's taking the graph of x to the 4th and reflecting it across the x-axis, which is going to make the graph open down and to the left and down and to the right. Okay, so you guys need to be mindful of that whenever sketching the graphs of polynomial functions. Okay, and we're going to piece everything that we've talked about together in the last set of 2 examples that we're going to look at. Okay, so we'll take a look at that in the next video.